Okay, hi guys. So for this next topic, we're going to discuss heat and temperature. So earlier in the semester, we learned about something called um, energy. For example, there was something called kinetic energy, KE. That was equal to 1/2 times the mass of an object times its speed or velocity squared, right? In this section, we're going to talk about a different kind of energy, and that's the energy of heat. Now, if we remember from kinetic energy, when you multiply 1/2 times mass is in kilograms, so it has units of kilograms. This is units, and speed, or velocity, is in meters per second. So the units of energy are kilograms times meters squared divided by seconds squared. And this is called energy units, and it has a special name called a joule. Now, when we're going to talk about heat, what we'll see is that heat is also measured in joules, but usually instead of joules, they use a different unit called the calorie. 1 calorie is equal to about 4.2 joules. So, or maybe it's 4.1 joule, it doesn't matter really. When you look on your food package, you usually see kilocalories, or 1 kilocalorie, when usually you're talking about food in your cereal box or whatever. 1 calorie there is usually a kilocalorie, which means 4,200 joules of energy. Those are joules, for joules for energy. So when we're talking about heat, we we want to keep in mind the units. It's units of energy. Heat is energy. But how can we define heat energy? It's not so simple, really, because what is heat? Really, it has to do with the motion of small molecules within a substance. So it's sort of the average kinetic energy of the molecules, but there's millions and billions of molecules in different objects. In order to understand heat, let's consider the following situation. You have a hot plate here, and this can make 2 cups of water get very hot. Okay, so you have a cup of water here, and let's say there's, some water here. That's M1. So some water. And then you have another cup here, which also has some water in it. Let's call this cup M2, but there's going to be, like, say, less water in this cup, M2. Now, if we have a stove and we turn on the heat equally so that both cups receive the same amount of heat, what we'll see is that, let's say at the time t equals 0, the water here is initially at some temperature, T initial. And the water over here is also at the same temperature, room temperature, T initial. So before we turn on the hot plate, both cups have water. This cup has more water, this cup has less water. But both cups both of the waters are at the same temperature. Now, if we turn on the heat so that both cups receive the same amount of heat, then what we'll see over time is that if this is the heat that you apply to the cups, and this is the change in temperature to T of each cup, we'll see that it looks like this for M2, and it looks like this for M1. Where this is T initial, and this is, say, the final temperature here, change in temperature. So what does that tell you? It says if you have less water here, it will get hotter more quickly because M1 has more water. So this is kind of a way to think about the relationship between heat and change in temperature. And the full relationship, the change in temperature given delta T is T final minus T initial is equal to this, where this quantity C is called the specific heat. Now you notice that it's inverse, the change in temperature is inverse with mass. And that's because basically if you have more mass, it's harder to change the temperature, and that makes sense. This quantity is called the specific heat, and it tells you how much energy or heat do I need to raise the temperature of this water by 1 degree for 1 gram of mass. Sometimes people write this equation like this. Q equals M times the specific heat times the change in temperature. Okay? All right, so that's pretty good. What we want to do now is try to understand a few more things. First of all, the temperature is usually given in something called Celsius. So you might have a temperature equals 20 degrees Celsius. When we do our calculations, we're going to expect to be in the Celsius system, not in Fahrenheit. The next thing we want to look at is what sort of what can we do to analyze what's called calorimetry? Because the next lab that we'll be doing focuses on this topic. And you should check out the lecture notes I posted online on this topic. But the idea behind calorimetry is this. If we have an isolated system, the total energy in the system is constant. So basically, if I have a system with two objects, let's say this object is very hot, and let's say this object cold. Well, what can happen is that heat can transfer from this object to that object. And the law of thermodynamics there's a fancy law which says that heat always goes from hot to cold. Now that sounds kind of obvious. There's a couple laws of thermodynamics. One of them says that heat, Q, always goes from hot objects to cold objects. Now that just makes sense. You can't make a hot object more hot by putting it in contact with a cold object. That's just, it makes common sense. The other statement about the law of thermodynamics is that if you look at the total energy of this system, the total energy of this system is going to be constant. Energy of the total system is constant. Now that doesn't mean that the energy of this is constant or the energy of this is constant. It means that the energy of everything, these combined objects, heat can transfer between the two objects, but the whole system has a constant energy. So that's basic thermodynamics. There's basically two laws. One says that the energy of the total system is constant or doesn't change, is fixed. The other law of thermodynamics says that heat always goes from hot objects to cold objects. Okay? Now, for today's lab, what we want to do is use these laws of thermodynamics to try to explain some phenomena. And in particular, what the experiment does is the experiment takes an object, a piece of copper metal, and this piece of copper has a chemical element symbol, I believe it's Cu in chemistry. This piece of copper is going to be heated up to 100 degrees Celsius, or 212 degrees Fahrenheit. That's boiling temperature. So we take a piece of copper, we're going to take 50 grams of copper. And we're going to drop it into a cup of water. Here's the water here. And this cup of water is going to be at 20 degrees Celsius. And it's going to have a mass of water, which is 100 grams. Okay. That's a cup of water over here. And the experiment, we view the system as both the piece of copper and the cup. And in this system, heat is going to flow, Q, from the hot copper into the water because we're going to drop the copper into the cup of water and basically try to see what happens. Now we can actually get mathematical and really predict the final temperature of the combined system. And that's kind of the goal of calorimetry, to try to predict what's going to happen. Well, the way you think about this is we know that the heat, Q, you go back here, it's going to flow, heat is going to come out of this hot copper piece of metal, and all of that heat is going to go into warming up the water. So we can say that Q equals the mass of the copper times the specific heat of the copper times the change in temperature, right? But we know we're given that we have 50 grams. We don't know yet the specific heat of the copper. That's basically, the specific heat is a parameter that tells you how easy it is to change the temperature. And then, first of all, we know that the initial temperature is 100, and we know that it's going to get colder, right? So we know that this is basically TF is going to be less than 100, right? So we know that that's going to be a negative number. So let's write it like this. TI to signify that this is the heat that is coming out of the piece of copper. That will be a positive quantity, okay? But we know that this T initial is going to be 100 degrees Celsius. So let's put that there. So this is the amount of heat that comes out of the copper. And we don't know what temperature the copper, remember, we're going to basically drop this into the water. We don't know what temperature it will end up with, but we do know that the same amount of heat acts to raise the temperature of the water. So for the water is going to go up in temperature. We'll have the specific heat of water here. And then it will be TF minus TI, where the initial temperature of water is given as 20 degrees. So let's continue the calculation. At this point, let me just write that down, that this heat transfers into the water. We have 100 grams of water, heat of water, times the final combined system temperature minus 20 degrees Celsius. Now you know that the final temperature will be more than 20 degrees because of the first law of thermodynamics says that basically heat is always going to flow from hot objects to cold objects. That means that the cold water will go up in temperature and the hot piece of metal will go down in temperature. But this same energy that flows out of here goes into here. So basically we can equate these two equations. We have this equation here, this equation, which describes the heat flowing out of the copper. And then we have this equation, which describes the heat flowing into the water. This is the heat that flows into the water. That's the same heat. The heat that comes out of the copper heats up the water. That heat is going into the water. It's going out of the piece of copper. So that means we can set these two things equal to each other. So let's do that. We have 50 times the specific heat of copper times 100 minus T final equal to 100 times the specific heat of water times T final minus 20 degrees. So what do we want to do? What we're really trying to do is figure out, once this system has come to equilibrium, equilibrium means settled down, where you have the piece of copper inside, the water, once it's settled down and reached the final temperature after the water, after it's sort of reached equilibrium, we want to find out what that final temperature is. So what we can do is solve this equation by basically multiplying out. You multiply everything out and then you solve for TF. So let's do that. We have 50 times C, or 100, minus 50 final. This equals 100 times specific heat of water times T final minus 100 times heat of, sorry, I should have put specific heat of copper here too. Missed that term. 100 times specific heat of water times the initial temperature of 20, right? So now what you can do is collect terms. Let's put the TF terms together on the right. Let's collect these two terms. You have 100 T water times TF plus 50 times C copper, specific heat of copper, times times TF. I moved this over to that side, and then I rewrote it on the left hand side. And then over on the other hand side, we'll have 50 times heat of copper times 100 degrees. And finally, we'll have plus 100 heat of water, 20 degrees. Okay. So now we can factor out the T final over on the left-hand side. And then if you do it, let me just put it on a new slide so you can see better. This comes out to T final will be 50 times 100 is 5,000. So that's 50 times 100 is 5,000. 5,000 here, that's times specific heat of copper. Plus 100 times 20 is 2,000 times the specific heat of water. Divided by the coefficient, which will be 100 times the specific heat of water plus 50 times the specific heat of copper. So you have to do some work, but eventually you get that. You can use the fact that the specific heat of water is equal to 1, simplify it so that T final and also the specific heat of copper, I'm going to tell you what it is. You're not supposed to know it for the experiment, but I'm going to tell you what it is because in the experiment, you choose, here's how you do the experiment. You choose copper, and then you set it to 50 grams of copper. You set the temperature to 100, and you can cheat and see that the specific heat of copper is 0.385. You're not supposed to know that, but I just want to look it up. Is 0.385. You can put those into the formula so that you get TF is 5,000 times 0.384 plus 2,000 times 1, which is just 2,000, divided by 100 plus 50 times 0.384. So I'm just going to put those numbers in my calculator and see what I get. Let's see, 5,000 times 0.4, 1920 plus 2,000. That's 3920. So we're going to have 3920 divided by 100 plus 50 384. Sorry. Give me once. 19.2 plus 100. That's just 109. Should be just 119.2. So let's see what that comes out to. This should be the final temperature of the system. 3920 divided by 119.2. That comes out to 32.9 degrees. So now let's run the run the simulation and see what happens. We're going to choose 100 grams of water. Click Next. Initial temperature will be 20 degrees. Click Next. We'll show graph view. We'll run the experiment. We got. Okay, according to the experiment, the final temperature should be 23.5 degrees. So clearly I made a mistake. Let me just go back where I think I made a mistake here. Let's just combine things correctly. Let's see, we have 50 TF goes with 100. 100 this plus 50, that's fine. Okay, sorry guys. The mistake I made was that the specific heat here is for the not for calories. So when you do specific heat, you have to have it either in calories or in joules. So back going to the start, I told you that there's these things called calories and joules. I guess I erased it, but basically, one calorie C is 4.2 joules, right? So basically, I was off by a factor of 4.2 because the specific heat of copper, we should do it in terms of calories, and if you look it up in terms of calories, it's 0.0923, not 0.384. Let's put 0.0923, and then when we do the specific heat of copper, we should be able to just change that number there, and then our math should work out. So it should be times 0.0923 here, and times 0.0923 here. So let's do the calculation again. See what we get. So 5,000 times 5,000 times 0.0923 is 461. And then plus 2,000, you get 2,461, right? So we can put 2,461. And then on the bottom, it's going to be 100 plus 50 times 0.0923 plus 100, that's 104.65. So when we divide, what do we get? We get 2461 104.65. Okay, and this becomes 23.5 degrees Celsius. Okay, so I made a little mistake. The mistake that I made was the specific heat has to be in the right units. Specific heat of water is 1 calorie per gram per degree Celsius times gram. And the specific heat of copper is 0.0923 calorie per gram times degree. But if you do things in joules, you're going to get different results than if you use calories. We're using calories and degrees Celsius and grams. And you can see that predicts the final temperature is 23.5 degrees. And if we go back to our experiment, we see the final temperature of the system. This is the hot copper is losing heat, and it gradually these two pieces of materials reach equilibrium at 23.5 degrees, and you can see the calculation is able to show that pretty well. So sorry I made a small mistake there, but I wanted to give you guys some ideas as to how to do this lab. Let me know if you have any questions.